CEO of a company called Freenome, and we're really focused on curing cancer through early detection and intervention. But today, I want to focus more about what are the challenges of applying ML to cancer screening and genomics more broadly, which I think is an important topic to discuss, especially because I think AI and bio has been hyped, I guess, to put it mildly. And I think a reality is going to set in fairly quickly, and it certainly did for us about a year ago when we were encountering a lot of these problems that we had to address. But just to set the stage a little bit, I want to give you just a quick background on why cancer screening is so important. So the best treatments today for cancer, these are including the immuno-oncology treatments like PD-1, PD-L1, CAR-Ts. You've heard about some of these, I'm sure, give you about 30 to 40% chance of survival. Those are the best drugs that we have for cancer. The traditional methods like radiation chemotherapy give you less than 20% chance. But when we accidentally detect these diseases early, the chance of survival goes up 80 to 97%. And this is not just for skin and lung cancer. It's literally across all cancer types. If you detect it early, the chance of you surviving that disease is actually significantly better than if you detect it late. Unfortunately today, more than 80% of all cancers detected are late stage. So we talk a lot about curing cancer. Early detection is the way. So why isn't that happening today? Well, the existing screening methods suck. So you have PSA testing for prostate cancer, which has a false positive rate of 75%. You have mammography for breast cancer, which has a false positive of 50%, and that's giving it a lot of credit. You have colonoscopies for colorectal cancer, which is actually fairly accurate, but at least in the United States, of the people that are told by their doctors to go and get a colonoscopy, 20% of the people actually do it. Something about not wanting to have a tube shoved up their butts, right? And then you have CT scans for lung cancer, but oftentimes these things just happen too late because usually the patient's already coughing, they're symptomatic in some ways, and that can cause all sorts of problems. So a lot of companies, including Freenome, turn to a new solution to come up with a blood test that people can take with their regular physical from a standard blood draw to detect cancer early, when it actually can be cured. The reason why they went after blood is because the blood is a gold mine of information. There's all sorts of things that are actually free-floating in your blood. Cell-free DNA is DNA fragments that have been shed by your cells as they die. So that's one molecule that might be floating around in the blood. But there's also RNA, there's proteins, there are extracellular vesicles, there's all sorts of things that are floating around there that you could potentially use to detect cancer. One such suggestion was using DNA. But there's a technical issue with doing that with just cell-free DNA. And that's because DNA sequencing is probabilistic, right? That is to say, we don't have a DNA sequencer today that can literally start from one end of our DNA, go all the way across, which we have in the human genomes are 3 billion bases, right? We have no sequencer that can literally go all the way across the 3 billion bases and actually give us the sequence of that DNA fragment. We have to literally break it up into hundreds of millions of small pieces of DNA, like 150 base pairs, and sequence those individual pieces because that's the fidelity of our DNA sequencing technology today. If you're detecting DNA fragments from the blood, it's already fragmented. These cell-free DNA fragments are being broken up by the proteins in the blood. So you can actually sequence this, but then the problem becomes is you sequence them, and then you have to try to map it back to the reference human genome so you can essentially figure out what the sequence of the DNA from that particular person is. And that's a probabilistic process. And it looks something like this when you actually look at the data. It's just a pileup of A's, G's, and T's for every position. And you basically try to count up those A's, G's, and T's to try to figure out what is the sequence at that particular position. Right? So it's a pretty crazy process that takes a lot of data. But then there's really the major problem is that the signal coming from the tumor in early disease is really, really low. In fact, of the DNA fragments that you capture from the blood, less than 0.01% of those DNA fragments will actually come from the tumor cells that will actually carry the tumor mutations, right? So unfortunately, you have to collect a certain amount of blood in order for you to have that DNA fragment even present in the blood sample to be able to capture that mutation. And so if you do a standard 10 mil blood draw, you have 50% chance of seeing at least one cancer fragment, which is not that great. And so when you actually do the calculation the other way, how much blood do you actually have to collect to ensure 95% chance of seeing one of the fragments? And it turns out it's about a water bottle worth of blood. And that's not a practical test. And in fact, you can plot this out and say if you collect 80 mils of blood, you have only 56% chance of actually seeing one of these cancer mutations using this method. And in fact, you have to collect about 300 plus mils of blood, which is about 10% of the blood in your body, in order to actually ensure 95% chance of seeing one of these fragments. So obviously, looking at DNA fragments coming directly from cancer is not going to work. What else is there? Well, there's immune cells that are trying to attack the tumor. And the DNA coming from that, that's actually much more plentiful. In fact, it makes up 60 to 80% of the signal. But it's like really hard to deconvolute this because the microenvironment around the tumor with the immune cells is actually a very complicated thing. There's a lot of cells. The dynamics is not very well understood. So a lot of companies, including Freenome, is turning to machine learning and deep learning to try to deconvolute some of these signals. And now I would like to address why this is such a difficult problem. So most of you probably have seen this stereotypical example now of breaking an image down into 4 numbers, R, G, B, and A, breaking those pixels down and then convolving across those pixels to essentially detect higher order structures, eventually being able to tell whether this dog is whatever, 82% Samoyed or Papillon. I have no idea if I'm pronouncing those correctly. I apologize. So the conventional wisdom says, well, we could do the same thing in genomics, right? We can represent the genome with all the fragments that are mapping back to a reference genome. We can count up each position, A, C, Gs, and Ts. How many of them are there? And then we can essentially start convolving across those bases and then start detecting higher order signatures, right? Eventually being able to create images like this that's representative of the entire genome and the signatures associated with that. And then hopefully that will get us to an answer of cancer versus healthy if we label the data properly, right? Sounds relatively simple enough, right? Unfortunately, that's not how it actually plays out. Because on the left-hand side, the problem is relatively, it's in the category of what we call fairly low dimension or low P or low D, and versus high N, right? So like we have millions and millions of images that we can actually learn from with parameters that really range in the hundreds, especially if we can do some kind of dimensionality reduction on the images that are coming in. The genomics is the complete opposite problem, right? The number of parameters that you have across the genome is billions. 3 billion bases in your human genome, minimum, right? And then you literally have thousands of samples to try to answer that question because not a lot of people's genomes have been sequenced. But let's face it, with billions of parameters, even if we sequence every person on Earth, that's 7 billion data points, right? And that is a tough problem. It's what we call a low N, high D problem. Another issue with this is, let's say you try to do a dimensionality reduction, right? The standard ways of doing dimensionality reduction has to do with understanding something about the inherent structure in the data. For pictures, we sort of have an intuition of what's important in a picture and how the pixels associate with each other. The same thing, unfortunately, doesn't really hold for genomic data when you actually plot this out. Like, you don't really have an intuition of what is the structure between different bases. And as you sort of go out from, say, a single base, how do those relationships change? There is a hidden structure there. We just don't know what that relationship actually is. So it's very hard to do proper dimensionality reduction in this. And then I think one of the last problems that we're dealing with is really, with an image of a cat, we know that's a cat, right? And we know what the ground truth is here. With genomic data, we don't really have a prior intuition of what does a healthy genome supposed to look like versus a cancer genome, right? We have no intuition of that. And so not having a ground truth is essentially a double moving platform type of a problem, right? You don't even know if your model is actually getting at the right signal. And then if you get at the right signal, you don't actually know that the model is working based on that data because you don't actually know what the ground truth is. So what are some of the problems that have been solved in genomics? Because I'm sure you guys have heard, especially around NIPS time, that some people have been doing deep learning on genomics. So one example, so first of all, to be very clear, all of the examples of deep learning applied to genomics so far has really been what's called local subproblems in genomics, right? That is to say, they're looking largely at a very small section of the genome, so in this case, like 250 base pairs out of 3 billion. And they're looking across multiple different types of data sets. In this case, they're using different epigenetic markers to essentially smooth the signal that they're capturing using an assay called ChIP-seq. You don't need to know these details, but just know that they're essentially taking problems that are very, very easy to solve, relatively speaking, because they're essentially taking the feature space down from 3 billion to 250. And then they're trying to increase the signal that different types of data that they can input across those 250 base pairs. So more recently, Google announced that they have a genomic sequencer aligner that is based on deep learning. And that came out of one of their Google Brain groups, as well as Verily, and it's called Deep Variant, right? So classical callers in genomics, this is solving that, mapping the small reads back to the reference genome problem, that probabilistic problem. But again, this is actually a problem where they can essentially train the model, and then they can compare it to whatever ground truth they actually have for that particular base. So they're essentially doing it base by base, where they're taking the 3 billion bases down to a single space, and they're actually turning it into an image problem, right? And using sort of existing image learning problems to essentially do base calls by giving A, C, Gs, and Ts different colors, and then saying, for this base, what is it likely to be based on all the examples that you've seen and based on the ground truth that we compared it to. Unfortunately, what the problem that Freenome and other cancer diagnostics companies are working on is a global genomic problem, right? We're saying, based on this person's entire genomic information, does this person have cancer or not? And so feature space is a really tough thing to minimize. But there's even a more fundamental problem than that. Because it's a clinical assay, you're taking real blood samples. Who collects it? How is it stored? Which tubes were used to store it? What was the timing before that tube was spun down into an actual DNA sample so that it could actually be sequenced? How was it transported? And are the labels associated with it, whether it's cancer or not cancer, actually accurate? These are all issues that you have to deal with your training data if you're trying to solve these kind of global genomics problems. And I can tell you, based on our experience, the labels are not accurate. In fact, if you actually plot out the chromosomes, and this is what we're doing here, this particular data set was labeled male. And this particular one was labeled female. Now, I don't know how much you remember from biology, but there's something about males and females that's different in terms of chromosomes, right? And what you see here is this particular person has 2 copies of the chromosome X, right? This person actually has only 1 copy of chromosome X and 1 copy of chromosome Y. It's clear that the person on the left is actually a female and the person on the right is male. But the hospital that sent it to us labeled it the other way around. So we can detect male-male flips, male-female flips, or male-female flips and female-male flips, but we can't pick up male-male and female-female. So the ones that we can detect is actually 10% visible swaps in the labels, which means there's probably 20% overall. Can you imagine doing a learning problem where 20% of your training set is actually mislabeled? Right? That's the type of problem that you're dealing with in clinical medicine. So where does that leave us? Well, the base biology signal to learn from may not be there because you're not collecting enough blood. The global genomics problem is an extremely small data problem, right? And so you need to try to do something like dimensionality reduction or some kind of curated feature selection, but we don't know that much about the structure of the data. So that's a very hard thing to do. So we also don't know whether our models are working well or not because we don't know the ground truth. And then finally, we have countless of these confounders that are experimentally driven that could pick up all sorts of, that could cause the learning engine to pick up all sorts of noise that you wouldn't necessarily encounter in traditional learning problems. So how do we solve this? Well, we solve this by bringing together a lot of different skill sets and knowledge. So for the first problem, we actually experimentally validate that we're actually getting some of these signals. And there are ways to manually validate this using molecular biology. So we literally have molecular biologists check for every sample that's coming in whether we have any signal at all, right? We don't have to be very specific about what signal, but we do need to know that the biological signal is there. Prior knowledge can be used to actually drive biologically inspired features to do more targeted feature selection. But of course, this is kind of a complicated problem because if you look at biology and the way it works, it's a little bit gnarly. But it's a lot of manual curation of the data to essentially represent some kind of prior knowledge that we can essentially inform the posterior with. And then we actually generate or find out the ground truth. So in this case, we actually use different types of data. So we don't just use DNA, we actually capture RNA, proteins, and other elements from the blood that can actually give us orthogonality to the data so that we can confirm what the ground truth actually should be using all these different data types. And then, of course, quality control of the incoming data basically means that we have essentially created a machine so that humans don't have to be involved in the processing of the samples or flipping of the labels or any of these kinds of things. And unfortunately, that costs a lot of money. As Matt mentioned, we've raised a significant amount of money. This is one of the reasons why. And so finally, I think to get to enough data, to get to the highest accuracy test, you actually need to have a feedback loop. Because there's just not enough data out there that you can buy as a company to execute on sort of super high accuracy tests and to be able to generate enough data to do so. So we have this model currently that exists in biology where from the clinics we get the sample, we put it into a classifier, we return the results. But then what we're working on now with the clinics is once we actually get them back the results, they can confirm whether that person actually had cancer or not, and that can inform our classifier, and we can actually use that data set to bootstrap and train our classifier much more than it was before. Just to highlight to you what kind of numbers we're talking about, the largest clinical trial that hasn't been done yet but has been announced is 120,000 people. Last year in the United States alone, the number of people that should have gotten colonoscopies but didn't is 35 million people. Right? So if we're able to actually get this feedback loop going with the clinics, we're talking about an order of magnitude more data than what we currently use to train our models, which is absolutely needed to solve these types of problems. So I'll just sort of wrap up on this. You just need a truly multidisciplinary team because for each one of these data points, you're talking about molecular biologists, computational biologists, software engineers. You're talking about automation engineers, biz dev, clinicians, all of those things, all those people to sort of execute on these types of problems. And just so that I can actually show you what this actually looks like finally, we actually tracked this person across time between 2008 and today. And we've learned over time by looking at a ton of these. In fact, we've studied tens of thousands of these sets. And you can actually see, well, sort of skewed. But we've actually come up with a metric called molecular age. And we've actually plotted the relevant areas of the genome that our learning engine has defined to be indicative of cancer or no cancer. And the peaks represent areas of those instabilities. So if the outer loop looks like Kansas, you're relatively healthy. If it looks like New York, then you're relatively not healthy. So this person's actual age in 2008 was 40. He took today's cancer test, which I think this was PSA, and Freenome's test. And you can see as time goes on, the levels of instability increases, right? And in fact, in 2011 is when he actually developed cancer, and you can see that with the increase of the peaks on the outer front, and you can even see mutations associated with cancer. This is when the Freenome test would have detected this person's cancer. Unfortunately, this was a retrospective study because Freenome didn't exist in 2011, and today's test didn't catch that. But watch what happens over the next few years. You can see his levels of instability is out of control. His molecular age actually went from something in his 20s to pretty much 60, right? And so you can see that the metrics that we're already beginning to define, despite all these ML issues, are more accurate than today's tests. But they need to be further refined as we see more and more data to get a more accurate test over time. But for this particular patient, unfortunately, he was diagnosed in 2015 with fairly late stage cancer, and he passed away in 2016. But we're actively working on this problem. I hope this gave you some idea of why this is such a tough problem to solve with ML. And I would welcome any questions. Thank you.
So we ate a little bit of the Q&A time, so let's keep my question and let's go directly to anything that you guys may have.
I think there's one back there.
Over there. Hello. Hey, thanks for coming.
Sure.
What was your approach for dealing with the Lowend problem, and how do you plan on approaching that over time?
Yeah, so that was really focused, we were really focused on how do we actually get the D down. And we mostly use prior biological data that we have already established that's associated with cancer, that's associated with immunology and cancer, and use that to infer some kind of manual curation of the features before we actually introduced it into the learning engine. So we reduced the dimensionality dramatically. But even then, we trained multiple models with different dimensionality reductions that's biologically inspired, so that we were hoping that we wouldn't miss any relevant signals going into it.
Hi, I'm just wondering, since there are like tons of mutations in like breast cancer or lung cancer, have you tried to look at like driver mutation that's like happened first during the onset of the tumor, and then the driver mutations causes more likely of other mutations? So are you maybe like you're looking for like TP53
Sure.
kind of driver cancer?
Sure.
That might has some predictability.
Yeah, so there's a bit of a problem with that, right? The main question is not which mutations you look at, it's whether there's actually enough signal for you to find those mutations in early disease and from the blood, right? And the answer is no. So it doesn't actually matter what the mutation is. There's just not enough signal in the blood to actually be able to pick that up in early disease. So we actually go outside of the tumor and we detect changes actually that are happening in the immune system that's trying to attack the tumor rather than the tumor itself.
Hi, last week at NIPS, which had the most amazing gathering
Yes.
of all the interdisciplinary people. So there was a convergence as to machine learning and how this could actually involve, really enhance medical. And there were three areas: diagnostics, care management,
Yep.
and then the ideal holy grail of personalized, medicine.
Sure.
The number of years that all these experts who have been really fully involved in this sort of attached to each of them becoming a reality, I was really surprised and just wanted to get your view. So most of them said personalized medicine was really wishful thinking, like far away. But on the diagnostics, there was a convergence as to many, many more years. So I think we have been kind of all misled with IBM Watson and everything, but technically that it was impossible, they said. What are your views?
Yeah, that's a really good question. I think we tend to bunch of different types of problems into these three categories. We like try to force them into it, right? There are like very different problems, for example, within diagnostics. There's early detection, there is actual sort of diagnostic and molecular profiling of the tumor, there's patient monitoring during therapy, and all of those things are gonna have different outlooks in terms of being, how many years it's gonna take to actually execute on those things. Now, even within screening, which is what Freenome is focused on, depending on the indication that you're going after, whether it's colorectal cancer, breast cancer, or lung cancer, it's going to have a different sort of timeline in terms of getting those tests to market, because how we treat those diseases is very, very different. So just to give you one example, one of the reasons why we're working on colorectal cancer first is the follow-up step to detecting colorectal cancer from a blood test is to do a colonoscopy and actually excise the tumor. Right, that's actually a minimally invasive procedure that follows, whereas like for lung cancer, you're either doing immunotherapy or you're doing chemotherapy, you're doing something that's very traumatic for the body, which could be much more detrimental if you'd actually diagnose it wrong. So the burden of proof for certain types of cancers are much lower, and for certain types of applications are much lower, and those are gonna happen faster than the cases like precision medicine or precision wellness or these kinds of curated wellness tips may take many more years, because the burden of proof for those working and those being safe for humans is so much bigger, right? So we'll take a lot more time to generate enough evidence to convince anybody that those things are safe. Thank you.
Thank you very much.